Now, concept of rate of reaction. Now, what does it mean? Rate means variation of anything with respect to time. Now, whenever we are saying rate of reaction, it means that it is something which will tell you about how the reaction is progressing. Now, what does it mean? Now, whenever we prepare a sugar syrup, so whenever we are preparing a sugar syrup, have you observed your mother that certain water is taken, then in certain pan sugar is added and she start heating it. Over the period of time, the sugar will melt, but in between, you must have heard in your colloquial language whether it may, so there may be a different words in a different colloquial language just to understand whether that sugar syrup is ready or not. What your mother do? She just dip her finger, so one finger, in that particular sugar syrup for a fraction of second, and then she just try to see whether she get a single filament or not. If that filament is proper, then she understand that the sugar syrup is now ready. Likewise, whenever any reaction is started, how will you understand that the reaction is progressing? Number one. Number two, how will you understand that how fast it is progressing? And therefore, to understand how reaction is progressing, variation of measurable parameter with time is noted down or measured. The parameter represent the change in concentration or we may express progress of reaction with respect to change in value of that parameter with time. We may express progress of reaction or we may understand the progress of reaction with respect to change in value of that parameter with time. That parameter means which parameter? Measurable parameter. This measurable parameter is representative of or is directly or indirectly related with the concentration of the reactant, which is changing with respect to time. And therefore, either by measuring the variation of the concentration of reactant with time or concentration of product with time, or concentration of pressure with respect to time, or variation in the value of measurable parameter related to concentration with respect to time, we can note down the progress of reaction, we can understand the progress of reaction, and thereby we can determine the rate of reaction. Now, the parameter which are considered for determining progress or rate of reaction are: A, 1, concentration of reactant; 2, concentration of product; 3, any measurable parameter other than concentration, like 1, pressure, generally considered for gaseous phase reaction; 2, density, variation in density of reaction mixture. Now, whenever I was working in a Raymond Steel in an acid regeneration plant, to what the regeneration has occurred, that we used to track by measuring the density of that particular mixture. Then optical density, refractive index. So we may keep the track of the change in the value of the parameter, like concentration of reactant or concentration of product, or any measurable parameter other than concentration, like pressure. It is considered if we are considering the gaseous phase reaction, because for gaseous phase reaction, measuring pressure is the most appropriate term, because we can relate the total pressure with partial pressure, which is representative of the composition of the reaction mixture consisting of reactant, product, etc., etc. Then density of reaction mixture, optical density, and refractive index. Now, in this curriculum, we will be dealing with mainly the change in value of the reactant concentration or concentration of product, or change in value of pressure. Now, after understanding how the rate is measured, why the rate is measured, and which parameters are considered for evaluating the rate of reaction or for determining the rate of reaction, now let us try to understand the definition of rate of reaction, the different forms in which the rate of reaction can be expressed. After understanding that, we will try to understand how the rate is determined from the experimental data. Now, methods of expressing rate. Now, the rate is generally expressed, generally, in case of liquid phase reaction, by measuring the variation in value of concentration versus time. Now, let us try to understand exactly what the rate means. So, definition of rate of reaction. So, it is defined as change in number of moles of reactant or say product per unit time per unit volume per unit volume. Now please remember, this volume means the volume of reaction mixture, but it is the common practice to write simply a volume instead of writing it as a volume of reaction mixture. And as discussed earlier, sometimes it may be easy to track the change in concentration of product, or sometimes it might be easy and possibly accurate to measure the concentration of reactant varying with respect to time. So it is defined as change in number of moles of reactant or product per unit volume, per unit time, per unit volume. Now, suppose consider the reaction A gives P, where A is reactant and P is product. Therefore, the rate of reaction expressed in terms of reactant is known or termed as rate of disappearance. Rate of disappearance. Now, why rate of disappearance? Because during the reaction, the reactant disappear. That means it is consumed and therefore its concentration reduced. So we say that disappearance. So rate of reaction expressed in terms of reactant is known as rate of disappearance, and it is denoted as minus RA. R stands for rate, A stands for reactant, that is rate of reactant, and this negative sign because the concentration of reactant is decreasing, so final concentration minus initial concentration divided by the time interval will be negative. So in order to make it positive, the negative sign is taken. So because the rate cannot be negative, it is possible, or it is that it will decrease with respect to time. Why? Because the rate is function of concentration. So as concentration will decrease, the rate of reaction will decrease. So its value will change, but it will not be negative. Please remember. And therefore, in order to make it that value positive, this negative sign is used, and it is pronounced as rate of disappearance of A. Rate of disappearance of A. So rate of disappearance of A is the term used whenever we are referring to the variation in concentration of reactant, and it is generally the most popular method of uh, expressing the rate of reaction. Suppose if we are measuring the concentration of product formed with time, then the rate is expressed as rate of formation or rate of appearance. Suppose we are measuring the concentration of product with time, then the rate is expressed as rate of formation or rate of appearance, and it is denoted as, say, RP, where P stands for product, R stands for rate. So rate of appearance of product P or rate of formation of product P. Now, to understand the term rate more clearly, now we will see the definition. Now, rate of disappearance. So it is defined as the change in number of moles of reactant per unit time per unit volume. So minus Ra is equal to minus change in number of moles of reactant A, DNA per unit time. The mole change will require certain time per unit volume. Change in number of moles of reactant per unit time per unit volume, where Na is equal to moles of reactant A at time T. V is equal to volume of reactor. Now please remember, whenever I am saying volume of reactor, it is never actually in a real sense volume of reactor. It is rather volume of reaction mixture. But there is a common practice to call the volume of reaction mixture as a volume of reactor. But suppose if the reaction mixture volume is 300 liter, then you have to keep some vapor space. So you may be using the reactor of a size equal to 600 liter. So actual volume of reactor is 600 liter, but the volume of reaction mixture is just 300 liters, and that 300 liter is actually the volume of reactor we are referring to. That means even though we are calling it as a volume of reactor, but rather we are referring to the volume of reaction mixture. So Na is equal to moles of reactant A at any time T. Now you may write Na0. Na0 means moles of reactant A at time T is equal to 0. That means initial moles of the A will be equal to Na0. Na is equal to moles of reactant A at a time T, V is volume of reactor, and this can be further simplified. Say for example, for constant volume reaction. Now what is constant volume reaction? The reaction during which the volume of reaction mixture does not changes. Typically liquid phase reaction are known as constant volume reaction. So for constant volume reaction, minus Ra can be written or can be modified as say d of Na upon V divided by dt. Now this Na means mole, number of moles. V means volume. So mole per unit volume is equal to concentration, and therefore this is equal to minus dc by dt, where Ca is equal to concentration of A with respect to time t, or with respect to time t. Instead of that, you may write at time t. So, and Ca0 will be equal to concentration of A at time t is equal to 0. Ca will be equal to concentration of A at time t. Now, suppose if the reaction is carried out for 30 minutes, and if in a 30 minutes, if you have taken 10 samples, then every time the concentration of reactant measured after 0 minute will refer to Ca and T. But suppose if it is a first sample, you may denote it as Ca1 and time as a T1. If it is second sample, you may denote it as a 2 Ca2 and time T2 likewise. So this is how the rate of disappearance can be expressed. Suppose if we are measuring, if we are measuring concentration of product with time t, then rate may be written or expressed as rate of formation or rate of appearance. So let us define rate of appearance. So it is defined as the change in number of moles of product per unit time per unit volume of reaction mixture. And therefore, for the same reaction, I can write it as Rp is equal to 1 upon phi d n p by dt. Now you will note the change. Here, negative sign is not there. Rp, rate of formation of product, is equal to 1 upon v dnp upon dt. Here also negative sign is not there. Why? Because number of moles of product will increase with time. Initially, moles of product will be less or zero, and with respect to time, moles of product will increase, right? So, similar to the earlier example, if V is constant, then this Rp can be written as T Cp upon dt. So this V you can take inside. So Np upon V, mole per unit volume, is equal to concentration. And since we are referring to T, that is product, so that concentration can be referred as concentration of product, minus Rp is equal to dCp by dt. So in this way, the rate of appearance of product or rate of formation of the product can be expressed. Now, these are the simplest examples of the expression of methods of rate of reaction. Please remember, I am just saying rate of reaction. I am not saying rate law expression. It's different thing, right? That we are going to explain. Now, in this case, we were referring to the volume of reaction mixture. There may be some other variables which might be involved. Means here the basis was per unit volume of reaction mixture. There may be some case where surface area of catalyst or mass of the catalyst may be written in place of V. Here we are referring to volume of reaction mixture. In some case, they may refer to surface area of catalyst. They may refer to the mass of the catalyst, etc., etc. So in this way also, in that format also, you can express the rate of reaction. Now suppose if the surface area of the catalyst is considered, and say if I'm denoting it as, say, minus Rs, the rate of reaction expressed in terms of surface area, then minus, I will write it as Rs A is equal to minus 1 upon S minus 1 upon S dNA by dt, where S is equal to surface area. Now suppose if rate of reaction is expressed, or rate of reaction expressed in terms of mass of catalyst. Let I am denoting that as minus RMA. So that can be written as minus RMA is equal to minus 1 upon M dNA by dt. So if I have to correlate the rates which are expressed earlier in terms of volume of reaction mixture, in terms of surface area, in terms of mass of the catalyst, you can equate the common term. So if you consider this, then if you transfer this S to this side, it will be minus RSA multiplied by S is equal to minus dNA by dt. Likewise, if you transfer this M to this side, it will be minus RMA into M is equal to minus dNA by dt. Likewise, the earlier expression minus RA is equal to minus 1 upon V dNA by dt. So if that V is shifted to this side, then it will become minus RAV is equal to minus dNA by dt. So by equating minus dNA by dt term for all equations related to A, we can write minus RA into V is equal to minus RSA into S is equal to minus RMA into M is equal to, you may use some other variables. So in this way, suppose if you know the value of minus RA, V and S, you can find out the value of minus RSA. That is, you may express this rate in terms of rate of reaction in terms of surface area. If you know the rate of reaction in terms of surface area and mass, you may express it. You may calculate, or you may express the rate in terms of, or you may convert the rate in terms of rate of disappearance of A in terms of mass of catalyst fade. So in this way, the interconversion between the different forms of the rate can be made possible just by comparing the value of minus dNA by dt and remaining by shifting remaining terms to LHS, and so we can correlate the different forms of the rates like this. So in this way, in today's session, we have tried to understand what is rate of reaction, how it is expressed if we are keeping the track of change in concentration of reactant, how it is expressed if we are keeping the track of change in concentration of product. We have also seen the different methods of expressing the rate, either in terms of surface area of catalyst or in terms of mass of catalyst and their correlations between them. We have also seen that how the rate is measured. The rate of the reaction can be measured either by measuring the change in value of concentration of reactant with respect to time, or change in concentration of product with respect to time, or by measuring the variation in the value of any measurable variable which is related to concentration or the matter or the reactant. It may be optical density, it may be refractive index, it may be density. So in all cases, it may not be very easy to measure the concentration. So other than concentration, whichever parameters are useful for evaluating the progress of reaction, like pressure, refractive index, optical density, density of reaction mixture, the variation in value of all these parameters is considered for evaluating the rate of reaction. Now, in the next video, we will try to understand how the rate of reaction is calculated by the given concentration data or by given variation related variation in pressure and time, pressure with respect to time. The most common practice of understanding the progress of the reaction is to understand the variation in value of concentration of reactant with respect to time. But if the reactions are gaseous phase reaction, it is better to measure the pressure, or measuring pressure is most simple or most feasible thing rather than measuring the concentration. Or rather, you can take it as a general guideline that generally for a liquid phase reaction, we keep the track of variation in concentration of reactant with respect to time, and in case of the gaseous phase reaction, we keep the track of variation in partial pressure of the reactant with respect to time. Thank you very much.